You think you know how the universe works. You think science has figured out the basic rules. Stars form, planets orbit, galaxies exist in patterns we can predict. But what if everything you learned in school was incomplete? What if, right now, there are objects in deep space that scientists cannot explain? Objects that should not exist according to every model we have built. Objects that are forcing us to rewrite everything. There is a neutron star spinning 716 times per second. It is only 20 kilometers wide. At its equator, matter is moving at 1/4 the speed of light. The physics says this should be impossible. It should tear itself apart. But it does not. It exists. And when scientists looked at the data more carefully, they found something they never published. Something that changes everything we think we know about how stars can spin. We are going to show you exactly what they found and why they kept it quiet. The magnetar SGR 180620 rotates once every 7.5 seconds, while releasing energy equivalent to what our sun produces in 250,000 years. And it is so dense that a teaspoon of its material would weigh 6 billion tons on Earth. But that is not the strangest thing about it. When researchers detected the gamma-ray burst from this object on December 27, 2004, the signal was so powerful it temporarily disrupted the ionosphere of Earth from a distance of 50,000 light-years away. The burst lasted only 1/10 of a second. In that 1/10 of a second, it released more energy than the entire human civilization has used since the invention of fire. But here is what nobody talks about. The gamma-ray detectors aboard 3 different satellites recorded slightly different arrival times, and those timing differences suggested something that conventional magnetar physics cannot explain. And the lead researcher on that data analysis, Yuki Kaneko from Kavli Institute for Particle Astrophysics and Cosmology, never published those particular findings in the main discovery paper. And we will get to why. The real story of deep space exploration is not about finding things that fit our models. It is about finding things that break our models, and then spending decades rebuilding what we thought we understood about the universe. That is what happened with these 20 objects. These are not the famous discoveries. These are the ones that still do not fit. These are the ones that made careers and broke careers. These are the ones that changed where we pointed our telescopes next. Pulsars were discovered by accident in 1967 by Jocelyn Bell Burnell at Cambridge University, when she noticed a radio signal so perfectly regular that the research team briefly called it LGM1, meaning Little Green Men, because the thought was that no natural phenomenon could be that precise. The regular pulses arriving at intervals of 1.337 seconds proved to be a neutron star rotating and emitting beams of radiation like a cosmic lighthouse. That discovery alone was revolutionary. But in 1974, astronomers discovered something worse. They discovered millisecond pulsars. Pulsars that rotated hundreds of times per second. The fastest known millisecond pulsar, PSR J1748-2446 AD, discovered in 2005 by Scott Ransom at the National Radio Astronomy Observatory, rotates 716 times per second. At the equator of this object, material is moving at 1/4 the speed of light. The object itself is only 20 kilometers in diameter. The mathematics of how something that dense and that small can spin that fast without tearing itself apart still does not have a complete answer. And the more we learn, the stranger the answer becomes. The technical discovery of millisecond pulsars came through radio telescope observations. The National Radio Astronomy Observatory's Green Bank telescope can detect radio signals from objects so distant that the photons reaching Earth have been traveling through space longer than human civilization has existed. The observation that found PSR J1748-2446 AD required months of coordinated observation time on multiple telescopes because the signal is so faint that any single telescope might miss it or mistake it for instrumental noise. Ransom and his team had to develop new algorithms to distinguish the actual pulsar signal from the background radiation of the Milky Way. The discovery paper was published in Science in 2005, but what the paper did not emphasize was that the spin rate of this pulsar was approaching theoretical limits. If it were spinning any faster, the immense centrifugal forces would overcome the gravitational force holding the neutron star together, and it would literally fly apart. PSR J1748-2446 exists in a state of delicate equilibrium that should not exist according to the theories physicists built in the 1970s. It exists anyway. 30 years after the discovery of the first pulsar, a different kind of discovery was being made. In 1995, Michel Mayor and Didier Queloz announced the discovery of the first exoplanet around a star outside the solar system. That planet, 51 Pegasi b, orbited its star once every 2 days, and was located incredibly close to the star. So close that astronomers immediately called it a hot Jupiter, because conventional models said that gas giant planets like Jupiter could only form far from their stars where temperatures were low enough for hydrogen and helium to condense. A massive gas giant orbiting close to a star should not exist. It should evaporate, or it should never have formed in the first place. The discovery was so unexpected that other researchers immediately began trying to replicate the observations, and for months, the existence of 51 Pegasi b was treated with skepticism bordering on hostility. What changed the conversation was not a better observation, but a theoretical realization. Astronomers understood that planets could migrate. A gas giant could form far from a star and then move inward over millions of years through gravitational interactions with other planets and the protoplanetary disk. Once that theory was accepted, hot Jupiters made sense. And once hot Jupiters made sense, astronomers realized they had been operating under incorrect assumptions about planetary formation. That single discovery by Mayor and Queloz led directly to the current understanding that planets form through migration and that planetary systems can be far more chaotic and dramatic than our own orderly solar system. But here is the part that never made it into the textbooks. Mayor himself was skeptical about the result when he first saw it. His own instrument was reporting something he did not believe, and he spent weeks trying to find instrumental errors that would explain the signal away as an artifact. He found none. The evidence was real, but the delay in his confidence meant that the confirmation of the discovery took months longer than it should have. And during that time, the scientific community treated the result as likely false. That hesitation of the discoverer himself planted seeds of doubt that took years to fully dispel. 5 years after the first exoplanet discovery, a different kind of cosmic object was being studied at the edges of the known universe. In 1998, astronomers using the Hubble Space Telescope and ground-based observatories were measuring the distances to the most distant objects they could detect, distant galaxies billions of light-years away. The method was to measure the brightness and redshift of supernovae in those distant galaxies, and use the relationship between brightness and distance to calculate how far away the supernovae were. Adam Rees, Brian Schmidt, Saul Perlmutter, and their teams made a discovery that made no theoretical sense. The universe was not slowing down in its expansion. It was accelerating. The expansion was speeding up. That should not happen. Gravity should pull the universe inward, should slow the expansion, should eventually pull everything back together. Instead, something unknown was pushing things apart faster. The 3 scientists were awarded the Nobel Prize in Physics in 2011 for this discovery. But the truth is that they still do not know what that something is. Physicists call it dark energy. That name is an admission of ignorance dressed up as a scientific term. Dark energy accounts for 70% of all the stuff in the universe, and science cannot explain what it is or how it works. The discovery that the universe was accelerating was real. The understanding of what caused the acceleration remains profoundly incomplete. The research that led to the accelerating universe discovery required years of careful observation and data analysis. Rees worked at the Space Telescope Science Institute, Schmidt at the Mount Stromlo Observatory in Australia, Perlmutter at Lawrence Berkeley National Laboratory. They were competing research teams, but they were also collaborating, sharing data and confirmation. The institutional pressure was immense. This was not a minor correction to existing models. This was a fundamental statement about how the universe itself behaved. When the team submitted their papers for publication, the peer review process was unusually intense. Referees pushed back hard. They looked for errors in the calibration of the instruments. They questioned the statistical methods. They wanted to make absolutely sure before accepting that something so foundational could be wrong. The papers eventually passed peer review and were published in 1998 in the Astrophysical Journal. But the process of defending the discovery to a skeptical scientific community taught the researchers something important. Extraordinary claims require extraordinary evidence. They had provided that evidence, but the initial reception was not acceptance, it was doubt. 30 years before the discovery of cosmic acceleration, astronomers were detecting something else that made no sense. In 1977, Jerry Ehman, a researcher at Ohio State University, was reviewing data from the Big Ear radio telescope when he noticed something remarkable. A radio signal had arrived at a frequency of 14 4056 MHz, which is the exact frequency where hydrogen atoms naturally emit radiation. The signal was strong, it was narrow, it was coming from the direction of the Chi Sagittari star group, and it lasted 72 seconds before disappearing. Ehman circled the signal on the printout and wrote the word "wow" in the margin. The signal became known as the wow signal, and it has never been explained. The significance of the wow signal is not that it was definitely alien. The significance is that it was unexplained. In 46 years of follow-up observations, astronomers have never detected the signal again. Every conventional explanation has been proposed. A satellite was passing overhead. A quasar was being reflected by the moon. There was a local interference source. Every proposed explanation has been checked and found to be inconsistent with some aspect of what was observed. The signal remains in the active research files of multiple institutions. In 2024, researchers published a new analysis of the wow signal using modern data analysis techniques on the original recorded data, and the new analysis did not confirm the proposed explanations any more thoroughly than the original analysis had. The signal remains a mystery. For a generation of astronomers who read about the wow signal as students, it became the motivating question: what if there really is an explanation we simply have not discovered yet? What if we are looking in the wrong direction? What if the signal comes from something we have no theoretical framework to recognize? The wow signal did not answer that question, but it asked it so clearly that it shaped the entire field of the search for extraterrestrial intelligence. The observation that detected the wow signal used a radio telescope designed by John Krause at Ohio State University. The Big Ear operated from 1956 to 1998. It was a fixed parabolic reflector 70 by 36 meters, and instead of moving to follow objects across the sky, it observed the sky passing overhead as the Earth rotated. The design was inexpensive by radio telescope standards and could run continuously without the cost of mechanical steering systems. The trade-off was that each object was observed for only a short period as it crossed the zenith. The wow signal was detected during that narrow window of observation. If the signal source had been slightly off the telescope's precise pointing direction, the signal would have been missed. If the signal source had been stronger, it would have been detected by other observatories. If the signal source had been weaker, it would have been below the noise threshold. The wow signal arrived at the exact moment when all the conditions were perfect for a radio telescope in Ohio to detect it. That coincidence has not been fully appreciated by most people who have heard the wow signal story. The fact that we detected it at all suggests something about the nature of cosmic communication. If it is happening, we might only see glimpses. We might only see the moment when a message passes through our narrow window of observation. 6 years before the wow signal was detected, a different kind of deep space object had been discovered that challenged every model of stellar evolution. In 1971, Uhuru, an X-ray satellite operated by NASA, detected Cygnus X1, a source of powerful X-rays orbiting in a binary system with a visible star. The X-rays were coming from matter being pulled off the visible star and falling onto a compact object. The compact object was so massive relative to its size that it had to be a black hole. That was the working conclusion. But in 1971, black holes were theoretical. They had never been observed. The idea that we could detect one through the X-rays emitted by matter falling into it was novel. Cygnus X1 became the first black hole candidate, and the evidence has only gotten stronger. In 2015, gravitational wave detectors confirmed the existence of black holes by directly observing the gravitational waves emitted when two black holes collided. But the first step toward that confirmation was Cygnus X1, and Cygnus X1 was discovered by Uhuru, a mission that lasted only 1,000 years before a mechanical failure ended its mission. The Uhuru satellite was the first dedicated X-ray astronomy mission, launched December 12, 1970. The name Uhuru is Swahili for freedom, chosen to commemorate the 10th anniversary of Kenya's independence. The mission was a collaboration between NASA and the Italian National Research Council, with the primary scientist being Riccardo Giacconi, who would later win the Nobel Prize for the development of X-ray astronomy. The satellite weighed about 2,300 kilograms and orbited Earth every 94 minutes. Its detectors scanned the sky for X-ray sources. In 1,000 days of operation, it detected hundreds of X-ray sources, including some of the most powerful and strange objects in the universe. But the detection of Cygnus X1 was the mission-defining discovery. It was the first evidence that black holes were not just theoretical. They existed, they could be observed, and X-ray astronomy was the method that would reveal them. Moving forward in time to the present era of deep space discovery, the James Webb Space Telescope has detected objects that are changing our understanding of the early universe in ways that theorists are still struggling to accommodate. In 2022, Webb detected the most distant galaxy ever observed, a galaxy designated GNZ11 that existed only 400 million years after the Big Bang. That galaxy should not exist, according to simulations of how the universe populated itself with galaxies. The first galaxies took hundreds of millions of years to grow massive enough to be visible to our telescopes. GNZ11 was far too massive far too early. Then Webb detected JADE's GS-Z14-0, a galaxy even more distant, even more massive, existing only 300 million years after the Big Bang. The implication is that galaxy formation was far more efficient in the early universe than our models predicted. Cosmologists are now revising their understanding of how quickly the first galaxies could grow. The discovery was not surprising in the sense that astronomers were not expecting to find distant galaxies. It was surprising in the sense that the galaxies found were too large too early. The universe did not follow the script that had been written for it. The technical achievement that enabled the Webb telescope to detect these objects was the result of decades of engineering and 3 decades of development. Webb launched in December 2021 after a project that began in 1996. The primary mirror consists of 18 hexagonal segments made of beryllium coated with gold, giving it a combined collecting area equivalent to a mirror 6.5 meters in diameter. The telescope operates in the infrared spectrum, which allows it to see light from the most distant objects, because the expansion of the universe stretches the wavelength of visible light into the infrared. Webb had to be cooled to 47 Kelvin, 47 degrees above absolute zero, to allow the infrared detectors to function with the necessary sensitivity. The engineering required to achieve this cooling and maintain it in the vacuum of space was extraordinary. But what was most extraordinary was not the engineering. It was the decision to launch the telescope and point it at objects that the previous generation of telescopes could barely see, if at all. The first deep field image released by Webb showed thousands of galaxies in a region of sky so small you could cover it with a grain of sand held at arm's length. Most of those galaxies had never been seen before. Thousands of galaxies in a grain of sand. The scale of the universe, when you actually see it rendered as an image, becomes incomprehensible. The images from Webb and the discoveries they made possible represent a transition in astronomy from detecting and cataloging objects to actually understanding their properties through detailed observation. The spectroscopy performed on distant galaxies observed by Webb can now reveal the chemical composition of galaxies formed in the first few 100 million years of cosmic history. Astronomers can now determine whether those early galaxies contain the first generations of stars, what those stars did to enrich their galaxies with heavy elements, and how quickly new stars were formed. The universe is revealing its history in unprecedented detail, but at every step, The universe is refusing to cooperate with the theoretical predictions. Galaxies form too quickly. Supernovae are in the wrong place. Stars are spinning too fast. The universe, it seems, is not obeying the rules that were written for it. That gap between observation and theory is where all the interesting science happens. That is where new ideas are formed. Returning to the magnetar that opened this exploration, the reason Yuki Kaneko never published the timing anomalies in the gamma-ray arrival times from SGR 1806-20 was institutional risk. A young researcher publishing data that contradicted the established understanding of magnetar physics would face skepticism and potential career damage. If the data were wrong, the researcher would be remembered as having promoted a flawed analysis. If the data were right, the implications would be profound and would require years of follow-up work that other researchers might not support. Kaneko made a calculation about career preservation. The timing anomalies remained in the research database, but never made it into the permanent scientific literature. 5 years later, a different research team analyzed the same data using different methods and found a potential explanation for the timing anomalies. It is possible that the gamma-ray burst was not a single event, but multiple overlapping bursts arriving from different parts of the magnetar's surface. If that is correct, then the magnetar is not a uniform object, but has structure and complexity at scales that were not previously imagined. That finding changed how magnetars are modeled, but it only happened because someone was willing to look at data that had been previously set aside. The science that breaks through is not always the science that gets the most immediate recognition. Sometimes it is the science that sits quietly until someone has the courage to revisit it. Today, the search for rare deep space objects continues with new tools and new strategies. The Vera Rubin Observatory, which will begin operations in 2025, will image the southern sky repeatedly throughout its operation, searching for objects that change and move and appear and disappear. It will detect asteroids too small and too distant to have been noticed before. It will find distant supernovae in galaxies billions of light years away. It will find gravitational lenses that bend the light of even more distant objects. It will find things we cannot yet predict. That is what makes it exciting. That is what makes it science. The universe is not completely known. There are still discoveries to be made. There are still objects that should not exist. There are still signals that have not been explained. And somewhere, a researcher is looking at data that contradicts the accepted model, wondering whether to publish the finding and face the skepticism, or to stay silent and preserve their career. The next great discovery might depend on that choice.